Hello, students. Let's look at chapter 4, Gravitation and the Waltz of Planets. In this chapter, we will learn about the laws of gravitation and how they affect the movement of the planets. The main topics that you will learn in this chapter are ancient geocentric model, epicycles model, sun-centered model of Copernicus, Tycho's naked eye observations, Kepler's laws of planetary motion, Galileo's telescopic observations supported a sun-centered model, and Newton's laws and how they uh, explain the movement of planets. And then at the end, we'll learn about tides. So first, we'll learn about geocentric model. Today, we know about the solar system and that sun is at the center and Earth as well as planets go around it. But in ancient times, this was not known or understood. So the first idea, the first model that ancient people came up with was a geocentric model. Geo stands for Earth and centric is for center. So they thought that Earth was at the center of the universe and everything else was circling around it, including the sun, moon, planets, and stars. So this is an example of how they thought everything worked. This is a slight improvement on the celestial sphere model that we had talked about in the previous chapter. As you can see, there's this outermost sphere, which has all the stars embedded on it. And so instead of realizing that it is the Earth spinning, which causes everything to look like it's the sky is rotating, they thought that this celestial sphere was spinning. So here the Earth remains stationary and the celestial sphere spins, because of which we see the stars move. However, with more observation, it was found that not all the objects moved in the sky at the same rate. For example, the sun moved at a different rate, the moon moved at a different rate, the planets moved at different rates. So separate spheres were created for them, and those spheres rotated at different rates to match up with what the observation was. And the real reason for why this observation happened was because the stars are too far away. And so their individual movement doesn't show up as much, but the moon, the sun, and the planets are closer to us, and they are obviously moving. So their movement is more visible to us and differentiates in how we see them compared to the stars. So this thinking worked for a long time. However, there were some problems, and there was this problem of retrograde motion. As the astronomers observed the sky, it was found that generally the planets moved in the eastward direction in the sky. What does that mean? It means, for example, we are looking at Mars, and on a certain night in October 1, 2011, it is seen right next to the constellation Cancer. Okay, as some nights go, after a few nights, it has moved a little bit to the east. Again, with more nights, it has moved more to the east. And so in general, the planets seem to be moving towards the right against the constellations, against the celestial sphere. So that was a common movement of all the planets, and all the planets moved at different rates. So we could explain them as being on these different spheres, which are moving at different rates. However, the problem was that some of them seemed to stop for a little while, change their direction, move from east to west, then stop again, and then uh, resume their eastward journey. And so for this time, for this small amount of time, they went in the opposite direction of their normal motion, and that was called retrograde motion. So here in this picture, Mars does this from February 1, 2012 to April 1, 2012. That is called retrograde motion. And with this picture, there wasn't any easy way to explain why this was happening. So astronomers started wondering about it and trying to make some changes in their original description to account for this. So the first, one of the models that they came up with was circles upon circles model. And in this model, the planet itself was not only going in a circle, but it was going in an epicycle. So an epicycle is a circle whose center moves on this bigger circle, which is called the deferent. So as the center of the circle is moving, the planet moves on this smaller epicycle. Okay, and when this happens, the rate at which it moves on the epicycle is faster than how fast the center of the epicycle is moving. And what that means is that when the planet is on the inner portion of the epicycle, when the planet is on the inner side of the epicycle, then the combination of the forward movement and the backward movement, in that the motion on the epicycle wins. And so for some time, it looks like the planet is moving in a backward direction. So this was a hypothetical such a suggestion, an idea that maybe this is what is happening. But this was wrong. Okay, this was not the real reason. However, the thinking was so entrenched for a long time. This model is also called Ptolemaic model. An ancient astronomer, Ptolemy, had come up with this. This is the name, Ptolemy. And so this model was called Ptolemaic model. And almost for 2000 years, there was a very strong belief that this is correct. So they just tried to keep the Earth in the center, and they tried to make some changes so that it would fit the observation. But the problem was that in the real world, the Earth is not at the center. Instead, the sun is at the center. So all these changes didn't really satisfy. However, they tried to make these epicycle models, and they added more and more circles to match the observation. So this is called the circles upon circles model, or epicycle model. And I want you to remember these terms, the deferent and the epicycle. However, after more and more detailed observations were made, it was becoming clear that some change was needed. And so a new theory of heliocentric system. Helios is the name of sun, another name of the sun. So heliocentric system, some astronomers started to think that maybe the sun is at the center and the earth is going around it, and all the other planets are going around it as well. So this kind of thinking started to become more and more prevalent, and more scientists and astronomers started thinking that that was probably the case. So even though there were other scientists who believed this and had some ideas about it, it was Copernicus who completely explained this in a way that it was very convincing for at least a lot of other astronomers and scientists to accept that that was the case. He was the first person to work out the details of heliocentric system in which the planets, including the Earth, orbited the sun. And that solved many of the confusions, many of the problems, and especially the retrograde motion was a big problem. And by changing our thinking to look like this, the retrograde motion was explained in a very obvious manner. So this is how the retrograde motion works. Here is the sun at the center, and there's these planets that are orbiting, and we'll just pick two of these right now for Earth and Mars. So the inner orbit is the Earth's orbit, and the outer orbit is Mars's orbit. Okay. And both of them are circling around the sun in this sort of a counterclockwise direction. And those numbers 1, 2, 3, 4, all the way to 9, those are different points of time, and they show the different positions of Earth and Mars at those points of time. And then those yellow lines show the line of sight. So at 1, there are two locations of 1. One is the position of Earth, the other is position of Mars. And depending on the geometry and orientation, Mars looks like to be in this part of the sky, towards the right upper corner in this picture. That's where Mars looks like it is. Then as we move to 2, the Earth is moving, the Mars is moving as well. And it's moving to the left in this picture. And in this picture, east is also, the left is the east direction. So that is what we observe from night to night to night. As we keep observing the same planet and its position, after few nights, the position of the planet is more and more east. And that's why in general, Mars looks like it moves in the east direction. And all the planets seem like they do that. So that happens at 1, then 2, then 3. But once we get to 4, 5, and 6, that is where the Earth and Mars are running right next to each other in their orbits. And this is a property of the solar system, which you will learn a little bit more later on, is that planets that are in the inner orbits, their speed is greater than the planets in outer orbits. So the Earth moves faster than Mars. And when it is running right next to the Mars, at that point, the point of view changes very fast. So as you can see, those 3 lines of 4, 5, and 6. So that is the time when Earth is overtaking Mars. And so at 4, it still looks like Mars is more eastward, but then at 5, it looks like it moved a little bit to the west. And then at 6, it moves even more to the west. But then as the Earth pulls away from Mars, now it has overtaken Mars and it is getting to be somewhere slightly far away from Mars, then the relative motion between the Earth and Mars becomes less important, and we again start seeing the general motion of Mars, which is going counterclockwise and therefore looking east. So this is the explanation for the retrograde motion, and this is the heliocentric explanation. So if you imagine that the the description of the universe is that it is a heliocentric, the sun is at the center, then you can easily explain in a very logical manner how this retrograde motion would happen. And this is a very, very important point. Again, I keep reminding you that in the tests and exams, you could get questions which could be diagram questions, and this is a very suitable concept to be asked for a diagram question. So please practice drawing and labeling this properly. Okay, so as I said, Copernicus explained the heliocentric system very well, and so we'll talk about the details of it. So in this next diagram, we'll see earthbound observations of planets' positions relative to the sun. So this is something that astronomers before and during Copernicus's time had observed. And he explained how all of that fits very well, and he gave these names. So now we are looking at it from a heliocentric system, and in heliocentric system, the sun is at the center and all the planets are going in orbits around the sun. So let's look at some terminology. The planets, so obviously at his time, then he also figured out that some planets have smaller orbits than the Earth. They are closer to the sun, and some are further away from the sun. And so Mercury and Venus, they were known at that time, and they have a smaller orbit. They are closer to the sun. And so this is the terminology. They are called inferior planets because they are closer to the sun and their orbits are smaller. And then Mars, Jupiter, Saturn, they are further away from the sun than where Earth is. So they are called superior planets. Uranus, Neptune, they were discovered later. So at least Mars, Jupiter, Saturn were there. Now, when we use, so those are called superior planets. So now when we use this terminology, we can obviously apply it to Uranus and Neptune as well. So there's inferior planet and superior planet. And to explain some of these positions, these configurations, we just need to draw one circle for the inferior planet and one circle for the superior planet. So it's all about how the relative position of the planets looks like when we are looking at them from the Earth and into the sky. Okay, so there is this unique position if we draw this line which joins the Earth and the sun, and then we extend it on both sides. You'll see that dashed line. Again, a reminder that this is a very important diagram to practice drawing as well as labeling. Okay, so if we draw that dashed line, it intersects the inner planet, the inferior planet circle at two places, and it intersects the superior planet circle at two places. And wherever those intersections happen, those are important points, okay, important locations. So if we look at the blue circle, which is for the inferior planet, the two intersection points are called inferior conjunction and superior conjunction. So by now you have probably understood that inferior sort of means a smaller or closer, and superior means bigger or farther in this case. So there is two possibilities. There are two possibilities where uh, when seen from Earth, the planet could line up with the sun, and that is called conjunction. So whenever a planet lines up with the sun, and we could see that in the sky, if you track the planet, its position is somewhere away from the sun, and then you keep observing it. Sometimes it lines up with the sun. So that is called conjunction. Now, the inner planet can have two situations where it lines up with the sun, and one of those is called inferior conjunction, and the other is called superior conjunction. In the inferior conjunction, the planet is between the Earth and the sun, and in the superior conjunction, it is on the other side. Okay. Now, when we see the intersection of this dashed line with the superior planet circle, which is the red circle, then there is only one conjunction. So when the planet is going on the other side of the sun, that is called the conjunctions. There's only one conjunction, but on the other side, on the outside of the Earth's orbit, it comes and intersects with the dashed line. That one is called opposition. Why is it called opposition? It's called opposition because, as you will see, um, at that time, the planet is opposite to where the sun is. Okay. And actually, that is a very important opposition, because whenever a planet is in the opposition configuration, that is the time when it is closest to the Earth. So as we look in the sky, the brightness and the size of planets changes. Sometimes you may have heard in the news, especially for Mars, that this year or in these few months or these few days, Mars is going to look very big and bright. And that is because it is in the opposition position. And just from the geometry, you can see that how that would happen. And also, when the superior planet is in the opposition, it is at the highest point in the sky at midnight. All right. Then there are two other configurations for the inferior planets, and those are called the greatest eastern elongation and greatest western elongation. Okay. So when we look at the inferior planets, which are basically Mars and Mercury and Venus, they are always close to the sun in the sky. Obviously, in the daytime, it's hard to see. It's hard to see them. But if you remember that picture from the previous chapter on eclipses, there was this picture where the sun was in eclipse. Let me try to draw a little picture here to remind you of that. So there was a sun, but obviously at that time it was blocked by the moon. So a solar eclipse was happening. And at that same time, somewhere over here, it was possible to see Venus. Okay. So that is the location of Venus. Venus is always either to the left or the right of the sun. That's just how the point of view is because of its smaller orbit and when we look at it from the Earth. So it is either to the left of the sun or to the right of the sun. If it is to the left, then it has an eastern elongation. It is to the east of the sun. Okay. Or if when it is on the other side, then it is to the west. And those two situations are called eastern elongation or western elongation. Now, there is a maximum distance to the east that the Venus could be, and that is called greatest eastern elongation, and that you will find by drawing this tangent line, from the Earth to the circle, and where it touches this, that would be the greatest eastern elongation. And then same thing here, this is the greatest western elongation. And by drawing this diagram, we can understand greatest eastern elongation and greatest western elongation. So those are the times when it is most separated from the sun in the sky. And when it is separated from the sun in the sky, that is when it is easy to see Venus. So when it is at greatest eastern elongation or western elongation, in one of those situations, you can see it before sunrise, and in the other situation, you can see it after sunset. Okay, so the further away it is from the sun, the longer you will be able to see it in the evening. Venus has also been called the evening star. Sometimes the evening star, sometimes the morning star, because Venus you can only see sometime before sunrise or sometime after sunset. So during the parts of the year when it is visible after sunset, it is called evening star. And when it is at greatest elongation on that side, then you can see it in the sky, in the western sky, up to 2 to 3 hours after sunset. Okay. And the same thing happens. There's a corresponding greatest eastern elongation and greatest western elongation for Mercury. However, Mercury's orbit is much smaller, so it doesn't stay in the sky for too long. There's a short period of time for parts of the year where you can see it before sunrise, and a small time after sunset when you can see it. So this is a very important diagram which explains all the observations of what we see in the sky, of how the planets move when they appear, where you can see them. So please practice drawing this. Difference in earthbound observations and actual orbital periods of planets, synodic and sidereal periods. By now, you must have been have gotten more familiar with the word sidereal. We have used this in terms of differentiating between solar day and sidereal day, and then synodic month and sidereal month. Okay. So this has to do with trying to determine the period of a planet. What is a period? Period is the time a planet takes to go around the sun. Okay, so there is a real period of the planet. For example, for Mercury, the sidereal period is 88 days. That's how long it takes to go around the sun. For Venus, it's 225 days. For Earth, it's 1 year. Mars is 1.9 years. Jupiter is 11.9 years. As you keep going to the bigger and bigger orbits, the period just keeps on increasing for two reasons. One is just the orbit is larger, and secondly, also because the planets, as you go further out, they move slower in their orbit. So those two things combine to make these sidereal periods longer, so that when you get to Neptune, it's almost 165 years. It takes 165 years to finish an orbit around the sun. Now, why do we talk about synodic period? After a lot of improvement, development in our understanding, we were able to find these numbers. But you have to appreciate that it is very hard to find out the sidereal period just from being here on Earth, because we are observing the planets from here on Earth, but we are on a moving platform. The Earth itself is moving. So it's really hard to make that observation. But we could at least see, if we are talking about an inferior planet, we can observe when there is an inferior conjunction, when the planet is at an inferior conjunction, and then we could keep tracking it as it is moving. And it comes back here again in the inferior conjunction. So we would say, to us, it would look like it completed one orbit. However, here is the problem. When the planet comes back to its original position, and it has completed its orbit, that is the sidereal period, the Earth has moved. So when looking from Earth, we would actually not experience an inferior conjunction because Earth has moved. So the planet would have to move some more time until it catches up with Earth, and maybe that would happen somewhere over here. The Earth is over here, and the planet's new position is here, right? So astronomers observed from the Earth, and they measured the time from one inferior conjunction to the next inferior conjunction. And that was the period, but that was not the accurate period. That was a synodic period. That is what you would measure from the Earth. So we have listed that. However, the understanding of mathematics and geometry allows us to do some calculations and use the synodic period to calculate the sidereal period, which is the actual period. Right, so these are the synodic periods. For Mercury, it's 116 days. Venus, 584 days. For Mars, it's 780 days. Now, for inferior planets, we go from inferior conjunction to inferior conjunction to measure those synodic periods. But for the superior planet, we can go from one opposition to the next opposition. Okay, so for example, for Mars, it is 780 days. So if you will do the calculation, that's a little more than 2 years. So 1 year for Earth is 365 days, right? So 365 days times 2 is about 730 days. So about 2 years, 2 months. That is the synodic period of Mars. So Mars goes into opposition after that amount of time. It goes into opposition. So once there is an opposition, and you see the Mars quite bright and big, and then Mars moves from this position again after 2 years, 2 months, it will appear in the same place again. So that the astronomers were able to measure the synodic periods, and then I'll show you a calculation, a formula with which it's possible to calculate sidereal period by just observing the synodic period. Something else to notice as we are moving towards the more and more outer planets, the synodic period gets closer and closer to 365 days. And the reason for that is um, the reason for that is that these outer planets move so slowly that the Earth completes its orbit and comes back into the same position. So you go from one opposition to the next in a year, and that outer planet has moved barely. So the formula is this. There are two different formulas, but very similar, just with a difference of a plus and a minus sign. If you're doing this calculation for inferior planet, then 1 over P is equal to 1 over E plus 1 over S. So S is the synodic period. This is what you would measure from Earth, and going from one inferior conjunction to the next inferior conjunction, or from one opposition to the next opposition. This is what you would observe, but that is not the true period. But you can use this formula to calculate P, and P is the sidereal period or the true period. And so for inferior planet, it is 1 over P is equal to 1 over E plus 1 over S. Whereas for superior planets, it's 1 over P is equal to 1 over E minus 1 over S. Okay, so these were all the methods by which the details of how the solar system works were figured out. So if you're trying to adopt a new system, you have to have a good understanding where you can explain everything and describe and explain everything satisfactorily and do the calculations. And that is what would convince that this is true. Let's talk a little bit more about the history of how our understanding of astronomy developed. So one of the big contributors in the understanding of astronomy was Tycho Brahe, and he lived from 1546 to 1601. He was someone like a big researcher, a big professor. Nowadays, we have these famous and very knowledgeable professors doing big research projects. He was a similar kind of person in his time, and he had his state-of-art measuring laboratory at Uraniborg, and he did very good measurements, very accurate measurements. So he did these very precise and detailed measurements, and he wrote books and made these detailed records, which he was very famous for. That was a big contribution to astronomy. And later on, he was what you would call an experimental astronomer. So he was doing more experiments. What is interesting is that even the telescopes did not exist during his time, and he used other methods to make measurements of the sky and record the positions of the stars and planets. And after he made all these records, he wanted to understand why the planets and the stars move in the way they move, especially planets. If there are some laws and principles that guide the movement of planets. So he gave all these records and details to his student, Johannes Kepler, and who was a mathematician, who was a theoretical astronomer, and he asked him to make sense of it and come up with laws of planetary motion, which Kepler did. All right, so next in the history of astronomy comes Johannes Kepler, and his contribution was he used the records created by Tycho Brahe and he came up with laws of planetary motion that describe how the planets move about the sun. He was the first to realize that the orbits of planets are ellipses and not circles. So even now, we think a lot of lay people who are not astronomers, who haven't taken astronomy as a subject, they think that planets go around the sun in circles, but in reality, those are ellipses, and we'll talk about what ellipses are. Ellipses are some shapes which look slightly different uh, from perfect circles. So we'll talk about the three laws. First, we'll talk about what ellipses are. So ellipse is a shape like this. It's more like a squashed circle. So that's a general shape of an ellipse. How can you draw an ellipse? We can make use of a string to draw an ellipse. Just like you can use a string to draw a circle, you can take a string, attach it to one center point, and then just uh, draw around it, keeping the string tight. You will get a circle. Instead of that, you could have 2 points, and you can make a loop from a string and go in this manner around, and you will be able to draw an ellipse. There is some terminology for the different points there. This line along the longer side of the ellipse is called major axis, and then these 2 points are called focus, and then half of this line is called semi-major axis. Okay. And then there is a property of ellipses which is called its eccentricity. Okay, and eccentricity could be different. Some ellipse could look very close to the shape of a circle, and its eccentricity will be 0. In fact, if it's perfectly 0, then an ellipse is a circle. So circle is a type of ellipse. If the eccentricity is a little bit more, the eccentricity goes from 0 to 1. Okay, so let's say the eccentricity is 0.2. Then the circle looks a little bit squashed. If it's 0.3, 0.4, it looks like this. If it's 0.5 or 0.6, it looks like this. 0.7, 0.8, it will start to look like that. All right, so eccentricity, it's called eccentricity. Let me write that word here. And its value goes from 0 to 1. So what he said was that the orbits of planets are ellipses and not circles. Okay. And however, something else to realize is that these orbits are ellipses, but they are ellipses with a very small eccentricity. So they could look very close to like the shape of a circle, but if we are being precise, they are ellipses. And in calculations, in mathematical understanding, we have to be precise, and so we have to treat them as ellipses and with the properties of ellipse. So here is the Kepler's first law. Kepler's first law says that a planet travels around the sun along an elliptical orbit with sun at one focus. And so that's another important thing, that sun is at one focus. It's not in the center of ellipse, but as you saw, there are 2 focus points. And so the sun sits at one ellipse. Now, this is a very exaggerated picture. In reality, none of the planets has such a highly eccentric elliptical orbit, but this is just to prove a point, to clarify a point. It's made in such a way that sun is quite to one side. At least that makes it clear to you that because of this, sometimes the planet is a little bit closer to the sun, and sometimes it's far away. In fact, the closest point is called perihelion, closest to the sun, and the farthest point is called aphelion. Okay, now comes the second law. The way Kepler wrote his second law, it was more geometrically explained. First, I'll tell you what it really means. What it really means is that when the planet moves through a region where it is closer to the sun, it moves through that region very fast. Its speed increases. And when it is far away, it moves somewhat slowly. In fact, the speed and the distance are inversely related. When it is far, it's moving slowly. When it is close, it's moving fast. Now, that's just talking in words, right? Scientists need to know numerically, be able to calculate how fast or how slow it moves, right? So for that, to be able to do that, Kepler explained it in this way. An imaginary line joining the planet and the sun sweeps out equal areas in equal intervals of time. Okay, so as you can see, A and B, let's say this period is that of 1 month, A to B. Now, because the distance is greater, even a small movement from A to B can create this area. Whereas when the planet is closer to the sun, because the distance is less, this triangle shape that is forming, its base needs to be bigger in order to match that same amount of area. So at that time, the planet will move more in the same time. That means it's moving faster. Okay. So that's how he described it, his second law. An imaginary line joining the planet and the sun sweeps out equal areas in equal intervals of time. And what that means is that the planet moves faster when it is closer to the sun. The third law, it is best expressed as a mathematical formula. P squared is equal to A cubed. In words, it means that the period of planets with bigger orbits, the period is larger, as you saw in that table of sidereal periods, right? The sidereal period of Mercury is 88 days. The sidereal period of Venus is, I think, about 8 months. The sidereal period of Earth is 12 months or 1 year. The sidereal period of Mars is 1.8 years. And as you keep going further out, the period keeps getting bigger and bigger. So again, that is in words, just saying that there is a relationship. It's bigger and bigger, but this formula actually allows you to calculate how much that period will be. So there's a relationship between semi-major axis. Semi-major axis is a measure of how big the orbit is. So remember that major axis was the distance along the long dimension of the ellipse, and then half of it is semi-major axis. So if this is the elliptical orbit, then about this is the semi-major axis. And it is denoted by A. Okay, so the formula is p square is equal to a cubed. So here they have written the periods represented by p in this first column here. In this first column here, they've written the periods in years. So in this formula, the period should always be written in years. And the semi-major axis should always be written in astronomical units. Only then it works in the way it is written. So the Mercury's period, which is 88 days, about 3 months, that's a little bit less than a quarter. So when you write it in years, it would be 0.24. Okay. Earth's is 1 year by definition, 1.88, and so on. So these are all the periods, and this column here is p square. You square those numbers, and you get this. And here are the semi-major axes written in astronomical units. And then here is the a cubed. And you can see how those numbers are the same. So p square is equal to a cubed. For each planet individually, p square is equal to a cubed. So he noticed that pattern. So he wrote that formula that p square is equal to a cubed. Okay. All right. So this chapter, we are talking about gravity, the motion of planets, and we are also talking about historical contributions. So another great contribution was that of Newton. He gave his uh, laws of motion. So this is not laws of planetary motion, but laws of motion. And these describe the motion of things anywhere. Okay, not just planets, but anywhere. And he showed the motion, how the motion of objects on Earth, those same principles can be used to describe the motion of planets. So I'll skip a few slides here, and you can read those these on your own, but I'll get to this. So what was the contribution of Newton? Newton is often credited with the discovery of gravity. Well, he didn't quite discover gravity. The first person who discovered gravity was probably someone who fell off a cliff. So people knew uh, that people and things and objects fall towards the ground. They knew that. So that was not something that had to be discovered. What Newton found was the universal law of gravitation. So he had come up with this idea of centripetal force. He found that anything that goes in a circular path, it has a force coming from the center, which keeps it in that circular path, and that force he named centripetal force. Then he looked at the moon, and he saw that the moon goes in a circle around the Earth, and according to his law, nothing could go in a circular path unless a force is continuously acting on it. Okay. So he saw that uh, he saw that the gravity of the Earth pulls the apple to the ground, So there is a force acting towards the center of the earth. It acts on the apple, it acts on other things. And then he saw the moon above his head, and he saw that it goes in a circular motion. So there is some kind of force that is acting on the moon and keeping it in a circular path. And that force comes from the center of the earth. So he made the connection. That the is it possible that the same gravitational force which pulls the apple to the ground, that same force goes all the way to the moon and is also responsible for keeping the moon in the orbit? And he did some more calculations, and he proved that that was in fact the case. And he came up with the formula which would describe how gravitation works. So his contribution was finding the universal law of gravitation. He took the gravity from the earth and he extended it to the moon, then he extended it to the sun, and he extended it to the whole universe. And there is a thought experiment that Newton described, which was called Newton's canon. And I have attached in the modules, there is a link where you can see the simulation. But the basic idea was that if you go on a very high hill and from there you shoot cannonballs at different speeds, if you shoot it at a very small speed, it will just fall to the ground and you would see the effect of gravity. That is what you expect gravity to do. You shoot it a little bit higher speed, the trajectory will be B. Again, understandable. Then you shoot it a little bit faster, it will go on the trajectory C. But as you keep increasing the speed, there will come a time when it will go on the trajectory D. And suddenly this has changed from the parabolic trajectory of just going a little bit distance and falling to the ground. Now it has changed into an orbit. So in the orbit D, the object is essentially just continuously falling towards the center of the earth, but never really hitting the surface of the earth. So it is able to complete a circle. That's how he described that the same gravity that just makes things fall to the ground, it can cause objects to go in orbits. All right, we are getting to the last topic here now, which has to do with gravity, and that is called tides. So tides are the regular rise and fall in the level of water in ocean. That is called tides. So every day, if you live near the seashore of an ocean, every day, twice in the day, the level of water rises to the maximum, and that is called high tide. And then in between those two times, it falls to the lowest level. The water recedes, and that is called low tides. So why are they caused? People observed that it had something to do with the moon. Somehow the moon was causing this. And a very simplistic kind of explanation is that when you have the high tide, the moon's gravity is pulling the water up. Okay, that's a very simplistic explanation. And there's some truth to it, but we'll explain more how this works. So first you have to think about the tidal effect. And that we'll understand by this hypothetical situations. Imagine there is a planet and there are 3 billiard balls which are being affected by the gravity of the planet. Now the red ball is the closest to, so it experiences the highest amount of gravity. The blue one, medium gravity, and the yellow one, the least gravity. If you release them, they will start falling towards the planet. The red one will move the most distance, blue will move the medium distance, and yellow the shortest distance. But if you look from the point of view of the middle ball, it will seem that both the red and the yellow ones are trying to get away. And if these three balls were attached together with some kind of an elastic material, then the effect this differential gravity would have would be to stretch this along the direction of the gravity. So that's important. Stretching along the direction of gravity, that is called the tidal effect of gravity. Now let's look at the how the gravity of the moon works on the Earth. And these different arrows show the strength and the direction of gravity of the moon on Earth. Okay, so the closest area has the greatest gravity, the furthest one has the least gravity, and then on the sides there's this medium gravity, but it is also pointing at an angle. If you average those out and remove the average, and you just draw the differences of those. So from the perspective of the center of the Earth, there is sort of a stretching along the line joining to the moon, and perpendicular to it, there's a compression. This is called the tidal effect. So this is what the moon tries to do to the Earth. However, this force is not strong enough to stretch and squeeze the Earth. So Earth's shape remains as it is. However, the water in the oceans gets affected by this. And so along the line joining to the moon, this region here, the water rises up. This region, water rises up. And here the water falls. Here it falls. Okay, so high tide, high tide, low tide, low tide. So at any point of time, two big regions on the Earth are experiencing high tide, and two other big regions are experiencing low tide. And as the Earth spins, and moon pretty much remains in that same place, doesn't move a lot, but the Earth spins one full circle, then the different regions of the Earth go through these high tide and low tide, and that's why twice a day there's high tide and twice a day there's low tide. What the most surprising thing must be for you, if you didn't know about this, is most people have some kind of an inkling that it's the pull of the moon that causes the high tide. So you would have definitely expected the high tide to happen on this side, but the fact that high tide happens on the opposite side too, that must come as a surprise. But that is an interesting fact. So this one is a little bit long chapter, but we are getting to the end. Here's a drawing showing how the level of water, this is an exaggerated picture, but how the level of water is high on the two sides, the high tide and low tide. But as the Earth spins, those different areas of the Earth pass through high tide, then low tide, then high tide, then low tide, each of them separated by approximately 6 hours. High tide, then 6 hours later, low tide, then 6 hours later, high tide, and then low tide again. Now within high and low tides, so it's primarily moon that causes the tides, but sun has some effect too. Interestingly, the effect caused by the sun is much less powerful, and that is because the way this tidal effect works, it falls, the strength of the tidal effect falls much faster due to distance. So even though sun is much bigger and much more powerful, its distance from the Earth is also large. So sun has some effect, and what sun can do is it can intensify the tidal effect, or it can dampen it a little bit. So in situations where the sun, earth, and moon are aligned, um, either the moon is on the opposite side to where the sun is, that would be a new moon, a full moon situation, or if the moon is in between the earth and the sun, that would be the new moon situation. And in both of those situations, the sun and moon work together to make the tides very intense, and those are very high tides. Those have been given the name spring tides. And when the geometry of the sun and the moon is such that they make a right angle with the earth, those would be the phases of those would be the times when the moon is in the first quarter or the third quarter. Then the sun just dampens the effect of the tide, and so the high tide is a little less high, the low tide is a little less low, and those are called neap tides. All right, so with that, we get to the end of the chapter. These tides are quite important. This chapter is about gravity, and it's on the large scale in the universe, gravity is the most important force. And so this tidal effect um, works in a lot of places. As you will learn more, you will see how many places this shows up. And here is a picture of two galaxies which are colliding, and the gravity of one of the bigger galaxy, that's the one on the left, is causing a tidal effect on the galaxy on the right, and you can see that it has been deformed. It's been stretched a little bit. All right. So with that, we finish this chapter on gravitation and the waltz of planets.